Today, we're diving deep into a systems failure, kind of like a forensic investigation. We're looking at a critical but almost completely invisible piece of infrastructure. What we're talking about is the hidden heartbeat of our biggest buildings, and what happens when that heartbeat just stops. So picture this. It's the middle of a brutal heat wave. The city is sweltering and an entire skyscraper's climate control system suddenly dies. Thousands of people are inside. What do you think the culprit is? A massive power grid failure? Some kind of natural disaster? Well, the truth is, it's usually something way less dramatic, but it's just as devastating. More often than not, it's a failure buried deep inside the building's cooling system. Specifically, a component that's just humming away up on the roof, totally out of sight and out of mind. To really get what went wrong, we've got to meet the main character in our story, the cooling tower pump. This thing is the unsung hero, the workhorse that's responsible for keeping these massive structures from turning into ovens. And this is it. Its job sounds pretty simple, right? All it has to do is lift water. But it's a relentless, brutal task. It's fighting against the fundamental force of gravity, 24/7. And this is where all the trouble really begins. Now, to understand why this specific pump is so vulnerable, we need to talk a little bit about physics. Don't worry, we'll keep it simple. It all comes down to the difference between an open-loop system, which is what a cooling tower is, and a closed-loop system, like you'd find in a building's heating. See, in a closed loop, the system is balanced. The water that gets pumped up eventually comes back down, and the weight of that water coming down actually helps the pump push the next bit of water up. It kind of cancels itself out. But in an open cooling tower, that water gets discharged at the top. There's no return trip to help out. That means the pump has to physically lift the entire weight of that water all by itself. It is a much, much tougher job. Okay, so our pump is already overworked from the get-go. Now, let's introduce the first villain in our little drama. Air. It's the silent killer that can sneak into the system and cause, well, catastrophic damage. Here's the best way to think about it. When air gets into the suction line, the pump's impeller suddenly goes from pushing dense, heavy water to, basically, nothing. And then, a split second later, it slams back into water again. This creates these violent, irregular shock loads. It's literally like giving the system a mechanical heart arrhythmia. And the consequences? They are incredibly severe. This is not a minor problem. The source manual is crystal clear about this. It says large quantities of air will break pump shafts in remarkably short order. We're not talking about long-term wear and tear here. We're talking about shearing a solid steel shaft clean off, and fast. So how does this killer even get inside the system? Well, believe it or not, one of the most common ways is through a totally avoidable but disastrous mistake that happens right when the system starts up. Let's walk through that chain reaction. This all happens in just a few seconds. The pump kicks on and it immediately starts sucking water out of the tower's basin or pan. If it pulls water out faster than the system can return it, even for a moment, the water level drops. And then, wham, a vortex forms, just like the one in your bathtub drain, but way more powerful. And it starts gulping air directly into the pump's suction line. And just like that, the arrhythmia begins. Air is bad, for sure, but it's not the only threat. There's another, more sinister killer at work here. It's a problem of pure physics that happens inside the pump itself, and it's called cavitation. So, to get cavitation, we first have to understand this thing called NPSH, or net positive suction head. Let's just simplify that. Think of NPSH as a pressure safety margin. Every single pump needs a certain amount of pressure at its inlet to keep the water it's pumping in a nice, stable, liquid state. So what happens when that pressure drops too low? When that safety margin, maybe because of a bad system design, just completely vanishes? You get this. Cavitation. Now, this sounds totally impossible, but the super low pressure inside the pump can actually cause the water to boil, even at perfectly normal temperatures. Tiny bubbles of water vapor, steam, just spontaneously form inside the pump. And trust me, these are not harmless little bubbles. As these tiny vapor bubbles move through the pump, the pressure rises again, and they violently collapse. They implode. Each implosion acts like a tiny, focused explosion, delivering a hammer-like blow against the pump's impeller. We're talking millions of these little explosions just eating away at the metal, literally destroying the pump from the inside out. All right, so we've identified our two killers, air and cavitation. Now, let's switch gears from forensics to prevention. The technical manual gives us what I like to call a detective's toolkit, a set of really clear, actionable rules to design a system that actually protects its own heart. And here they are, 4 golden rules. And notice they all focus on one critical area, the pump's suction line. Rule 1, just leave it alone. Don't put anything unnecessary in it. Rule 2, keep the pump below the water level so gravity keeps it flooded with water. Rule 3, design the pipes so air can't get trapped. And Rule 4, and this is a big one, do not put fine mesh strainers where a simple clog could starve the pump. Okay, those rules are a fantastic start, but protecting the pump really is a team effort. We also have to look at other parts of the system, like the bypass piping and the whole filtration strategy. Okay, just take a look at the bypass piping. A really common mistake is to pipe the bypass directly back into the pump's suction line. This is super risky because it can create a low pressure point that literally sucks air into the system through any tiny leak. The much safer recommended design is to send that bypass water back to the tower basin. It's a simple change, but it completely eliminates that risk. And now for filtration. You know, strainers are absolutely essential, but where you put them is critical. And I mean that. Putting a strainer in the wrong place can be even more dangerous than not having one at all. A clogged strainer can ruin even the most perfectly designed system. So here's the smart strategy. First, you protect the pump. Use a coarse, large mesh strainer right at the tower pan. It'll stop the big stuff, leaves, debris, whatever, and it's easy to clean. Then, you protect the really sensitive condenser tubes by placing your fine mesh strainers on the discharge side of the pump. That's the high-pressure side, where they can't possibly starve the pump of water. And that really brings us to the core takeaway of this whole thing. After all the complex physics and the piping diagrams, it all boils down to 2 really simple principles. Protect the pump's suction from air and protect it from any unnecessary loss of pressure. You do those 2 things and the heart of your system will just keep on beating. So the next time you're in a big building on a hot day, just remember that invisible workhorse humming away on the roof. Its health really depends on a smart design that respects the simple but completely unforgiving laws of physics. That system has a heartbeat, and now you know how to listen for it.